פחות או יותר. כן. טוב, אז שלום לכולם. לי קוראים ארז קרפס, ואני למעשה פה בעיקר כדי להציג את ה... זה המיקרופון הזה. כן, אוקיי. אז מה שאני הולך להציג זה בעיקר, אך ורק, הדוקטורט של אייל טייטלר, שעשה את הדוקטורט בהנחיה שלי ושל Per-Olof גוטמן. אז אייל הוא, אם היינו מחכים חודשיים, הוא כבר היה חבר סגל פה בתעשייה וניהול, אבל כרגע הוא עדיין בפוסט-דוק בטורונטו. אז אני פה להציג את מה שהוא עשה. ודבר ראשון, אני רוצה להקדיש את המצגת הזאת לאיליה יוסלוביץ', ה-co-author הרביעי שלנו, שהוא מומחה עולמי לבקרה אופטימלית ברמות שאני לא יכול להסביר אפילו, כי אני לא יודע על בקרה אופטימלית כל כך, אבל לשמחתי היה לנו את איליה ואת פר ואת אייל שהם עשו את כל החלקים האלה. אוקיי, אז על מה אני רוצה לדבר איתכם? אז אני רוצה לפתור בעיות קבלת החלטות, כמו בעיות שקשורות לתחבורה חכמה, תזמון של רמזורים, או ניהול תנועה בצומת, בעיות של רובוטיקה, כמו מה שצריך לעשות ה-Mars 2020 רובר, כן, הידוע בכינויו Perseverance, שהוא צריך לנסוע, לאסוף דגימות, לשים אותם וכן הלאה, או בעיות של חקר ביצועים, של נגיד שליטה על מיזוג, או שליטה על power levels, או כל מיני דברים כאלה. אני רוצה לפתור בעיות כלליות, בעיות תכנון וקבלת החלטות כלליות, ומה שמשותף לכל הבעיות האלה, כן. מה שמשותף לכל הבעיות שאני רוצה לפתור, זה שאני יודע את המודל, אוקיי? אני יודע את הדינמיקה, אני יודע איך המערכת מתנהגת. אם אני אעשה ככה, יקרה ככה, אם אני אעשה ככה, יקרה ככה, אם אני אעשה ככה, יקרה ככה. ואני יכול למדל את זה על ידי איזשהו influence diagram. כן. אנגלית. אוקיי, no problem. So I can model my knowledge of the dynamics of the system and how do they behave using an influence diagram. And these problems all feature a mix of discrete and continuous state variables and decisions, right? So you can say something like, I want to drive left at a velocity of 4.32 meters per second, right? That is a continuous action, right? I can choose my velocity. Or I can say something like, if I'm in Tel Aviv, I want to park, otherwise I want to increase my speed, right? So I have some dynamics here which are mixed. And of course, the real world, we have things going on concurrently, and we have some uncertainty, which I will, hopefully I'll get to. I mean, if I had 30 minutes, I would have gotten to it. Apparently now I have 22. So we'll see. Okay. So we want to do autonomous mission planning. And here is, I hope I can play this video without the mouse. Okay. So think of a motivating scenario where I have a big ship, and the ship can launch drones, and I can control the ship and the drones, and the drones want to deliver presents, let's call them presents, to different locations. And this problem features a mix of discrete and continuous, right? So the positions and the velocities of my agents are continuous variables, right? But whether they visited some location or not is a discrete variable. It's true or false. And whether drone 1 is on board the ship or not is also a discrete variable, true or false, right? So I want to be able to deal with a mix of these. And maybe my objectives are to visit Paris and visit London and then finish at DC and with all the drones aboard the ship, right? And of course, I want to obey realistic constraints, right, about the physics, right? You know, the position is the differential. The velocity is the differential of the position, right? So I have physical constraints, spatial constraints, temporal constraints, and I want to make sure I obey them all because otherwise the solution wouldn't be executable in the real world. So I'm afraid I don't know how to play this video here. But basically the video illustrates a plan, right? So the kind of ship flies and it launches the drones and the drones go here and another drone goes there and then they all meet up. And it's really nice, but I don't know, it's not working. Okay, so how do I model these problems? So I can model them as a hybrid planning problem. And the hybrid planning problem has several components. So I can look at the set of discrete propositions. You can think of them as control modes, right? So and a full assignment to the discrete variables to the propositions gives you a control mode, basically a dynamical system. And when you change the discrete variables, you change the dynamical system, right? Then you've got the continuous state variables, so think, you know, position, velocity. You've got discrete activities. You've got the initial state and the goal. You've got some control variables like acceleration or velocity. And you've got your objective function. So this is pretty big. And here's a very simple model of such a system. So you've got actions unload, navigate, mine, and visit. You've got constraints that govern the transitions between these modes. You've got the dynamical system in each of these modes. The details are not important, right? It's just, you can look at this as a hybrid concurrent automaton. If you're so inclined, you don't have to. I prefer not to, but okay. So what I want to do is generate a feasible plan, right, from the initial state to some goal state, and hopefully maximize my objective. So what's the problem? Well, it's a difficult problem to solve, right? So even classical planning with only discrete variables is p-space complete. And if I want to just add time, right, so just one continuous variable for time, I go to x-space complete. And in general, the problem I want to solve is undecidable, okay? So you can have an infinite state space, and you can easily create undecidable problems. But of course, that doesn't mean that it's not hopeless, right? You can still solve problems from a class which is undecidable, which is what we do here. Okay, so here's an example of how to model the problem I showed you, right? So my discrete goals are which locations I want to visit and what objectives I want to achieve. I have my dynamics here, which I can describe using this differential equation. I don't know if you like differential equations. I don't, but unfortunately, I work with these controls people, and they seem to like them. And I want to optimize, let's say, the total power I use in my plan. Or I want to optimize the combination of these. Okay. So how am I actually going to solve this, right? So I'm going to take my hybrid planning problem. I'm going to generate an approximate solution. I'll explain how in a minute. And then I'm going to check. If I fail to generate even an approximate solution, then I can give up, right? If I can't solve the simplified problem, then there's no solution to the real problem. If I do find a solution for the approximate problem, then what I do is I verify it using the full specification of the problem, right? So I check if the solution is feasible in the real system. And if it is, then great, I'm happy, I have a feasible plan, then I can do some sort of trajectory optimization and return the plan. Otherwise, I can search and try to find different variations of this plan, right? So if I'm able to do that, then great, I can still do the trajectory optimization and return the plan. If I can't, if I'm able to prove that any variation of this approximate solution isn't feasible, then I go back and I do a plan elimination. I tell my approximate solution, okay, don't give me plans that look like this, but give me other plans for the approximate solution. Okay, so this is kind of the big picture, and now I have slides about each of these colored boxes, and I'm going to start going through them, and then when it's time to stop, I will stop. Okay. So here's an example. It's a very famous temporal planning problem. So I have a cellar, and in my cellar I have a fuse box, and the fuse, one of the fuses has blown, and I need to fix it, right? So to fix the fuse, I need light. But of course, the fuse is blown, I don't have power. So what I do have is a single match, right? So I can light my match, and it gives me light for 10 seconds. And replacing the fuse takes 7 seconds. So what should I do? Well, it's pretty easy, right? So I need to light the match. And while the match is burning, I want to replace the fuse, right? So this is what's called required concurrency in temporal planning, because I must have two actions executing at the same time. Makes things difficult for some planners, but I can actually just look at this as a sequence of what we call snap actions or instantaneous happenings, right? So starts and ends of actions. So I can start light, then I can start replace, then I can end replace, and then I can end light. Right, so this is my plan. And I can find that plan by just searching over the sequences of snap actions, right? And then I can encode the solution as what's called a simple temporal network. So it's basically a set of linear inequalities. So this comes before this, and this comes before this, and this comes exactly 10 time units before this, and this comes exactly 7 time units before this. And we can formulate this as a linear program and solve it. Okay? So this is the approach I showed you applied to temporal planning. In my postdoc, I worked on something like this for hybrid planning, where we assumed we can control the velocity. So using first order linear dynamics. I won't go into the details, but basically we create a second order cone program which solved a continuous part of the problem. So we search over the discrete actions, over the snap actions. Each of these planned skeletons gives us a continuous optimization problem, which we can solve using a convex optimization. And we get this, and we solve it. And here we assume that we control velocity, right, like I said. So in the problem that we're interested in solving here, we want to solve, so this is our approximate solution, right? Because in the real world, we don't really control velocity, right? We can't change velocity from 60 kilometers per hour to 90 kilometers per hour instantaneously, right? We have acceleration we need to worry about. So what we do is we start by assuming we can control the velocity directly. And then we get the solution, right? And we try to find a feasible trajectory which does account for acceleration that follows the solution, right? So this is the solution verification step. So the planner I showed before, it's called Scotty, might give you a trajectory that looks like this. You kind of just go at time 0 to a velocity of 4 meters per second. But in reality, what you want to do is you want to accelerate to 5 meters per second, right? Keep that velocity until time 6.5 and then slow down, right? And that will give you the same, that will still be a feasible solution. It's slightly different, but you'll still reach the end of this segment of the plan at the same time, right? So that's the idea. We want to take the initial position, the initial velocity, the final position, the final velocity, and the time, and check whether there is a realizable plan, a physically feasible plan which achieves this. So I warned you, controls people. We formulated this as an optimal control problem and solved this. I say we, I don't know what they did. But Pontryagin maximum principle was used. And there's some equations here. And more equations. I'm really, just for everyone's sanity, I'm going to skip these. But you can look at the papers if you're interested. Or you can ask Ayal when he gets here. But we solved this, and we have a closed form solution. Just plug this into your planner and everything will be great. It's not recommended, but you can do that. So good. So we know how to verify if the approximate solution is actually feasible or not. So moving on to the blue box of trajectory optimization. So we got a plan. And we know that it's feasible, but it's not necessarily optimal, right? So in the verification, we just wanted to make sure that we satisfy the constraints on time. When we're doing the trajectory optimization, we're actually optimizing both time and energy. So we have some factor alpha, which tells us what the trade-off between time and energy is. And we... It turns out that when you set alpha to 0, you get some weird phase transition, which is interesting. And again, more equations, but we can do the trajectory optimization, and all is well. Of course, the problem is that maybe the plan skeleton I got from the approximate solution is infeasible, right? But so the solution I got is infeasible, but maybe the skeleton, just the sequence of snap actions, is okay. And what I want to do is, right, so maybe my simplified dynamics told me I can go here and then here and everything will be fine. But of course that won't work, okay? But I don't want to disqualify the plan skeleton which says go to this region and then go to the goal because maybe I can do this, right? So we want to do some sort of a continuous search. We can actually encode this as a neural network. We don't care about learning, but the neural network is a very nice function approximator, so we can do that and do this. And then finally, if we determine that skeleton is invalid, then we can tell our planner to just don't give us solutions that look like this. And this is good. And I can't play the videos. Of course, it's not done because we have, things like wind and waves that we can also account for. More equations. Yeah. Okay. So, and there's even more work to do. Yes. I don't know if we have time for questions. Yeah.
So, when you talked about to reject to check if the approximation is feasible.
Yeah.
And you started by you can control the velocity and then the acceleration, but you might skip over because of all of the equation. But does you also deal with the fact that also the acceleration is not constant? Because in the graph you showed, like,
yeah,
it was,
so you're talking about third order jerk and whatever. I mean, it's possible. We haven't done it, right? Because we have a closed form solution for the dynamical system where you assume you can change the acceleration, you control acceleration directly. If you can't, then you can formulate a higher order dynamical system, and I don't know if we'll be able to give it a closed form solution or not, right? But you know, in principle, the high level approach is feasible, would work. Yes. Sorry. Yeah.
Can you go back to the slide where the mechanism is presented?
Yes. Yeah. Yes.
So you said that so you encode the problem using as an optimization problem, and then you try to find a feasible solution. And then after you have a feasible solution, you try to optimize it. So
Yes.
you improve.
Yes.
Okay, so my question, I have maybe two questions. So the first one is, how do you use, if you can tell it shortly, how you can convert the optimization method such that you can use deep neural networks to solve it? This is one question. And the second question is, after you have a solution from this deep neural network, how do you know that this optimized solution is also a good feasible solution?
Okay. So I'll give you a brief answer. Essentially, what we have here is a nonlinear optimization problem. And a neural network is a nonlinear function. And the gradient descent, or whatever, the optimizer for neural networks, is something that solves a nonlinear optimization problem. So what we do is we manually create a neural network which encodes this nonlinear optimization problem, and then we use, you know, Adam or your favorite optimizer to solve it. Whether we can make any guarantees? No. No, it's nonlinear optimization, we can't. But we hope for the best, right?
Thank you very much.
Thank you very much.
Okay, thank you.